one proportion, z-test, which is utilized to compare the observed proportions with the hypothetical value. The chi-square test determines if our observed counts in a categories are significantly differ from our expectations. So this is very important. We will be having two different errors, and that errors is nothing but type 1 error, which is called as alpha, and second one is type 2 error, which is also called as beta errors. Hello everyone, I welcome you all to the second session of Unit 4, that's under Statistical Computing and our programming subject. This is a subject with respect to the NEP syllabus, and it's a 5th sem syllabus of BCA degree, correct? The 4th unit is all about statistical testing as well as modeling, and the things what we have discussed in our previous session. Let's see a quick recap of that. But before that, let me introduce myself. My name is Deepa Kutnikar. I'm working as an assistant professor at the Department of Computer Science, Vidhyaashram, Temple of Excellence, MYSURU. This is a quick recap of the things that we have discussed in our previous session, where it discussed like what is statistical testing, what is statistical modeling, and we did also discuss what is sampling distribution. So if we want to work with statistical modeling, then we have to understand the samples and we have to work with respect to samples. So for that sake, we will be learning like what is sampling distribution and how to arrange the samples with respect to probabilities and all. Then followed by we did discuss what is hypothetical testing, and in order to do the hypothetical testing, what are the components required or involved. So all these things we have discussed in our previous session, that's in session 1. And with respect to today's session, we will be dealing these things like we will be learning what are the testing means, testing proportions. Then we also do discuss testing categorical values, then followed by what are the different types of errors and what are the power. And we also do discuss the ANOVA, which is one of the important topic with respect to your exam point of view, that is all about analysis of variance. So these will be discussed in our today's session. So let's start today's session with understanding what is testing means. So testing mean is one of very important criteria, because we start our sampling by understanding or by calculating a mean of that samples. So whenever we do or whenever we prefer hypothetical testing, then the first step is to calculate mean. So over here, hypothetical testing can be done by initially considering the samples and calculating the means. So that is nothing but a testing mean. But in order to calculate that mean, or we can say population mean, which is represented by a mu symbol. So in order to do that, what is the criteria involved? So in order to calculate the population mean, we have different type of tests. So let's understand what are these tests. So the first one is one sample t-test. Here we go forward and calculate the mean of samples when the standard deviation is unknown and the number of samples are minimum. So at that point of time, we go forward with a test that is nothing but one sample t-test. And with respect to next one, that is two sample t-test, this is used for comparing two independent variables. So whenever there are two samples which are independent of each other, then at that point we can go with our two sample t-test. So these are two type of t-test. Okay. Next we have one more test to calculate mean, that is nothing but z-test. Now with respect to t-test, we did understand like whenever our samples are minimum or 2, then we go with the t-test. What if we have number of samples more than 2, but a minimum number only? Then at that point of time, we go with the test criteria, that is nothing but our z-test. So even here, if sigma is known or the sample size is large, okay, and the population is approximately normal, at these conditions, we go forward with a test, and that test is all about our z-test. In the sense, we can say it is completely opposite of one sample test. Yes, correct, right? So in one sample test, the standard deviation is unknown, but in Z test, the standard deviation is known and the samples for one test are minimum and the samples for Z test is large. Whenever the samples are large, then we can go with our Z test. So these are the tests along which we can go forward and calculate the mean of testing samples. Alright, that's why this is called as testing means. Up next, let's see what is testing proportion. Whenever we want to go forward and test a population proportion, that is P. So this population proportion we have discussed under the components of hypothetical testing. Correct? So do you remember that? If not, you have to go back and check our previous videos. Okay. So whenever we want to calculate or test with respect to that population proportion, that kind of test is all about testing proportions. Even here we have multiple tests like one proportion, Z test, which is utilized to compare the observed proportions with the hypothetical value. So there is some constant value which is called as hypothesized value. Okay, so that value will be considered and it will be compared with the observed proportions of the samples. So that is all about one proportion Z test. Second one, two proportion Z test, where it is used to calculate the proportions, but please note here, when the proportions of two independent samples. Whenever there are two independent samples, then we can go with two proportion Z test in order to calculate what? That is to calculate our population proportions, that is lowercase p. And whenever we want to go forward, we have to consider samples, right? Yes, sample size must be large enough, okay, in order to go with normal appropriate. So what about the samples? So we can consider it has np naught of n of 1 minus p naught. P naught is nothing but a proportion with respect to 0th sample, and it should be, yes, greater than or equal to 10. So it will be holding the samples from 0 to 10. So that's what nothing but our two proportion Z test. Up next, let's learn in depth like what is one proportion Z test. Alright, so let's start with the hypothesis structure because it is a constant structure which is considered, correct, in order to compare with our observed values. So the first one is H naught P. So H naught is a hypothesized constant value for 0th sample multiplied with our propagation constant P, and this both will be equal to the propagation constant, that is P naught of 0th sample. Up next, let's see for two-tailed Z test. We will be dependent on this, but we can say that this first value, that is LSB, will not at all be equal to the RHS will not be equal to the LHS. So that is with respect to two-tailed test, and with respect to one-tailed, we can say the propagation constant will either it will be greater than or it will be less than our initial propagation constant, that is P naught. So that is with respect to one-tailed test. Up next, let's see few of the R code options through which we can go forward and consider this one proportion Z test. So B binomial dot test is used in order to define our one proportion test, where we are defining the X and N, the number of samples, followed by P and P naught. For propagation constant, we are assigning the P with P naught value. Okay, for exact test, useful with respect to small samples. Please note, it is useful with respect to small samples. Up next, we have proportion dot test, where we are defining X, N is a number of samples, followed by P equals P naught. We are assigning the 0th as sample value with respect to P, where we are defining like it is correct. What? No, it should be false, correct? It should not be equal. Yes, that's what we have defined by using our Boolean expression for approximate or even the normal test. Up next is a two proportion test. Here we can see the hypothesis structure where we will be having H0, P1 and P2. Why P1, P2? Because we are dealing with more number of samples, right? So we need the proportion constant, okay? Up next, let's see what is that. So we can define our H1, P1 which will not at all be equal to P2, P1, and we can also say this P1 will not at all be equal to P2. Then we can also say P2 or P1, P2. So this is our two proportion Z test. Alright, up next let's see a expression with respect to our two proportion Z test. It is Z test, so we are assigning with respect to Z samples which will be equal to P1 minus P2. Here we can see that we are using or we are defining two of the proportion constants followed by P of 1 minus P into 1 by N1 plus 1 by N2. So this is a basic expression with respect to our Z test whenever we are dealing with multiple samples. Alright, let's move forward. So now we have completed our one proportion Z test, two proportion Z test. So totally we can say we almost are done with our proportion test. Up next, what's that? So by using that test results, we can do the sampling distribution. Alright, then we can make the decision like yes, with respect to these test values, we have got the successful samples and these are the samples which we have got by doing our sampling distribution, and finally we will consider the decision like yes, this is right and we'll be going forward with these number of samples. So that is with respect to visualizations. So let's see a small R code with respect to our visualization. So we will be considering proportions dot test followed by the samples, that is C of x1 comma x2, and we are assigning n with a vector n1 comma n2 followed by alternative, that is for two-sided. So we will be doing this R or the proportions test representation in both the sides. So this is small example with respect to our language. Now let's see, if we consider the samples and we have grouped the samples with respect to categories, up next what is that? We have to go with test, right? So that is testing categorical variables. So in order to do this, we'll be considering one of our crucial tests which is called as chi-square test. So now let's see what is this all about. So whenever we have few samples that are categorized and in that category the number of counts, that is observed number of counts, are like how it is it equal, is it different, or is it same? So these differences or these comparisons will be marked by this chi-square test, where we can see that if determine it, the chi-square test determines if our observed counts in a categories are significantly differ from our expectations. So this is very, very important. Now let's see what are the different key tests in order to do this, in order to note a difference between the observed counts as well as the expectations. What are the tests? So the first one is goodness of fit test, where we will be comparing the observed counts with the expected frequencies for a single categorical values or variable. So that is with respect to goodness of fit test. Next one is a test of independence, where it evaluates whether two of the categorical variables are related or not. Like if we consider an example of gender with educational levels. By using these two variables, we can just verify like these two categories, that is gender as well as our education, are related or not. So this is with respect to test of independence, where both the variables are totally independent and they are not dependent on each other. So we have a small expression with respect to that, which is x square is equal to summation of r. So whenever we consider very important test, so for that we will be defining few key assumptions, right? So in the same way, the chi-square test is one of a crucial test whenever we deal with our categorical values. Now let's see what are the assumptions with respect to this chi-square test. The first assumption is the sample observations are independent. The second observation we can see here, the expected cell counts, generally it will be greater than or equal to 5 for validity database. So this is with respect to the key assumptions where we can say that the sample are independent and also the cell counts will be greater than or equal to 5, that is directly correlated with a database. Up next, let's see a small interpretation of the same. So here we reject our null hypothesis of X. Why is it? As it exceeds some critical value based on our data frames, that is DF. So this is all about our chi-square test assumptions as well as our interpretations. Up next, let's see what are the different types of errors as well as the powers. Errors, there will be different types, right? Like we will be having different errors with respect to different categories, and whenever we will be dealing with some UIs, we have different kinds of errors. But when we consider the samples and the sampling distributions, or we can say directly whenever we go for statistical modeling, then we will be having two different errors, and that errors is nothing but type 1 error, which is called as alpha, and second one is type 2 error, which is also called as beta errors. Now let's see one by one like what is all about. The first one is a type 1 error, which is also called as alpha. So these errors are directly dependent on our null hypothesis H0. So let's see how is it dependent. If we have false positive, like whenever we say we are rejecting our null hypothesis, at that time we can go with our type 1 error. Next one is a type 2 error, that is beta. So this type 2 error is also dependent on our null hypothesis, where we can say that whenever the false negative, that is whenever we fail to accept the null hypothesis and it is false, then at that point of time we can define our type 2 error. So these are the two different types, that is alpha and beta, which are directly dependent on null hypothesis, where we can consider the rejecting null hypothesis is true. Yes, I am rejecting the null hypothesis, but in fact, that is in truth, the null hypothesis is been rejected. Then at that point of time, the kind of error what we define is called as false positive, which is nothing but a type 1 error. Alright. Second one is whenever we are considering that the null hypothesis is failed to satisfy, that is false. Alright. So that is false negative. So at that point of time, the error caused can be noted as type 2 error or beta. Up next, let's see what is the statistical power, which is all about 1 minus beta. Statistical power, it can be considered as 1 minus beta. So here we can note that it is directly dependent on our type 2 error. The power is directly dependent on the type 2 error. So the power is all about whenever the probability of correctly representing the rejected false null hypothesis, at that point of time the power generated, we call it as a statistical power, which is represented as 1 minus beta. Up next, let's see the trade-offs between the errors and the power. If we want to lower the type 1 error, at that time what happens, it reduces the risk of false positives. But if we consider this alpha and concentrate on reducing type 1 error, then we can expect the type 2 errors, that is of lower powers. Next one, power is improved by increasing the sample size as well as the effect size, or we can say by increasing alpha. So this is very, very important. So when the power is increased, whenever the sample size is increased as well as the alpha is increased, at that point of time, the power will also be increased. So this is two very important trade-offs. So this is with respect to errors and powers. Up next, one of the important topic with respect to your exam point of view. This is one of the most repeated question with respect to this unit, that is analysis of variance, which is also called as ANOVA. This is the analysis of variance. So do you remember variance? Now we have calculated variance with respect to our hypothesis testing, where variance is also a component under hypothetical testing. Okay, components. Now let's see like how to analyze this variance, that is by calculating mean. Yes, absolutely. If we calculate mean, it will be helpful in order to calculate our variance, right? Because the variance will be dependent on the mean values. All right, now let's see what is with respect to statistical technique. It's a statistical technique to compare means across three or more groups of samples by partitioning the variance. So we have to partition or group the variance as between the groups and within the group. So what are those two? Between the group and within the group. So if we partition our samples in these two variance parts, then we can say the variance can be calculated very easily and in a simpler way. So analysis of variance is a statistical technique, okay, in order to compare the means across three or more groups by partitioning variances. So we will be partitioning variance as between the groups as well as within the group components. So now let's see what is this F ratio. F ratio with respect to our ANOVA. So that is mean square of different variables whole divided by the mean square errors. Up next, let's see what is a advantage of this analysis of variance, that is it prevents inflation of type 1 error that arises from multiple t-tests. So the inflation that is occurred by our type 1 error, that is with respect to alpha, is being prevented by using this ANOVA or analysis of variance. Up next, let's see what are the different variants over here in ANOVA. So the first one is one-way ANOVA, where we will be considering only single factor, and with respect to two-way ANOVA, we have two factors and the interactions between them too. Up next, we have random and mixed effects models, which exist for more complex designs. So whenever there is a more complex design, then we can directly go with mixed effect models as well as random model. So these are the different variants. Up next, let's see what are the assumptions. So as we are analyzing one of important component, that is variance, we have to consider a few assumptions, right? Let's see what are those assumptions. The first one is residuals are normally distributed. All right. Next one, the homogeneity of variance across groups are maintained or calculated, and the observations are independent of the constants or the calculated values. So these are the three assumptions that deals with our ANOVA technique. Now, when we discuss the assumptions, then we have to discuss interpretations, right? Like after assumption and calculation, what are the different interpretations that we get from our ANOVA? So over here, the first interpretation is the p-value or the probability value from our F test. So we can define the p will be greater than or equal to alpha, that is our type 1 error or significant value, where it describes like rejection of H0, that is null hypothesis, means it differs among different groups. The second is post hoc test. This is like after significant ANOVA uses comparisons like Tukey or Bonferroni to identify specific group of differences. So these are the different two types of comparisons techniques, that is Tukey as well as Bonferroni. So these are the two different techniques in order to compare our variance, that is ANOVA, and in order to identify a specific group of differences. So this is a post hoc test as well as the p-value from F test. Up next, let's see like we have interpreted, but what are the different extensions that are possible? So the first extension is it uses Wells ANOVA, where when a group of variances are unequal, then a robust alternative or traditional ANOVA has to go forward or has to be calculated. This is with respect to ANOVA, where we define like what is ANOVA and then what is the expression for that, then followed by what are the two different tests in order to calculate the variance. Up next, we also did discuss what are the different assumptions with respect to ANOVA, and after assumption, the interpretation. Like, yes, we have considered the test, we have assumed, and now after that, what are the interpretation that is possible? And after interpretation, we did also understand like these are the things we get, and if the things won't come under our interpretation, the next level, what is that? That is the extension. So yes, all these things we have discussed with respect to ANOVA, that is analysis of variance. So this is all about ANOVA, that is analysis of variance. So these are the things that is included in our unit 4. All right. Thank you.